Hello, and welcome to Measuring the Internet in Real Time. Today, I'm going to be talking to you about how CloudFront measures the internet, how CloudFront measures all the traffic that reaches us, and why we do that. While we're doing that, I'm going to show you how our systems have been built in great detail, so you can also build your own feedback loops for your own distributed applications. So before I get into details, let me talk to you about CloudFront. What is CloudFront? You probably know it's a CDN, a content delivery network, and that's the map that shows us where we are today. A secret is that this map on our website is most of the time out of date. The text below is correct, but you're not going to be seeing in this map Palermo in Italy that we launched last week, or Denver in Colorado that we launched last week, because our marketing team can hardly keep up with the speed we build POPs. Last year, we built more than one POP a week, so it's very hard for them to keep up. I'm sorry I've been saying POP. That's one definition I'd like to go with you before I start. POP is point of presence, is a CloudFront data center somewhere around the world. Okay, why is it important that we are in that many edge locations? We are in 107 today. That's 97 POPs, 108, 97 POPs. The importance of that is the speed of light. So from here to São Paulo, which is where I was living before I started working for Amazon, it's 100 milliseconds RTT round trip time. If you do TCP handshake plus SSL handshake, those are 3 round trips. So you're 300 milliseconds before you start transferring any useful data to your customer, which is going to be sitting there waiting, and that's a lot. And that's in the best case scenario. If it's on a mobile network or something, it's going to be even worse. There's also the problem with bandwidth. Regional ISPs don't have the amount of bandwidth that is needed to transfer data back to your origin here in the US, or back to your origin in Europe, or whatever it might be. So we need these edge locations to be able to deliver data close to where those ISPs are and not to congest these international links or long-haul links on the internet. Even if those are not our links, someone is paying for those links, and these links would be congested otherwise. So who would benefit from CloudFront? First, whoever wants more performance. Every single one of those edge locations around the globe has a cache. So obviously, for static content, it's a no-brainer. CloudFront can deliver the data directly to your customers without not even going back to your origin, wherever it might be. But it's also good for dynamic content. Let me explain you why. First thing, sometimes we think of dynamic content as content that changes. Let's say a news site. A news site changes all the time because people are publishing new information, and you don't want your customers to be seeing the same news stories every day. But let's say you have like 1 million hits a day on your news site, and you use a very, very short time to live on your cached objects, let's say 1 second, right? I think it's okay for customers to be reading 1 second old news. That's pretty much okay, right? If you do that, and you have 1 million of requests distributed evenly across the day, that's a simplification, but that illustrates the point. You're going to have more than 91% cache hit ratio, which means more than 91% of requests are going to be served directly from the edge with that 1 second TTL. If you do a larger TTL, let's say 5 seconds, that should be okay for news. It's going to be even greater than that. But let's say your content is not cacheable at all. Let's say it's Amazon shopping cart, right? That's non-cacheable, or it's an API request. That's also non-cacheable. Even in those cases, having CloudFront will improve your performance. For instance, when Slack, I believe you all know Slack, started using CloudFront for their API, they started using us for DDoS protection. But they found out that performance was greatly improved. The reason for that is that all this TCP handshake and TOS handshake is done between your viewer and our edge location. So we are not incurring these 300 milliseconds for doing this handshake. After the handshake is complete, CloudFront POPs will have a persistent connection back to your origin. So you also go to a faster path. Why is it faster? So first, because this connection is reused across many, many requests from different users. And second, because this connection is kept hot. Hot in the TCP sense of hot, meaning congestion window and other TCP parameters are already optimized for this path. Also, if your origin happens to be inside one of the AWS regions, there's a very good chance your traffic from the CloudFront POPs are going to be riding the Amazon backbone, which is a global backbone, which is usually much better when it comes to congestion when compared to the public internet. So for these reasons, even for dynamic content, CloudFront can greatly accelerate your content. As I told you, we saw that with Slack, and more recently, Amazon, the e-commerce website, has started using us, and they also saw great performance improvements. CloudFront is also good if you want to have more availability. CloudFront has a lot of points of presence, so there's a greater chance that one of them is going to be reachable from your customer's point of view. All these points of presence have multiple paths to the internet. When you compare that to what would be a web server provider or a cloud provider, and we have only these many paths going back to this provider. When you compare a large CDN like CloudFront, we have all these multiple paths that can reach our POPs. If one of these paths goes down, the POP is still fully reachable from everyone. It's also, I put here DDoS protection, but I'll prefer to talk about what happens if your site becomes suddenly very popular. Let's say you got lucky, your blog post got linked by a very famous news site, or a very famous blogger, or a celebrity, or something like that. So the very day you're going to have your 15 minutes of fame, your site is down because it doesn't have capacity. That will not happen if you're using CloudFront. So for these very good days, you're going to have all the capability of CloudFront, all our power of serving terabits per second of data and millions of requests per second to your customers. Also, in the unfortunate case that your origin might be down, in that case, CloudFront will be able to service tail content, even if your objects are expired. So let's say there's something goes wrong with your origin, be that a static content or dynamic content. If we have this object in cache, your customers are going to be seeing old news, but they're not going to be seeing an error page, and that's way better. Third, CloudFront is also important if you want more security. So I mentioned DDoS on the previous one. CloudFront gives you standard AWS Shield as part of the CloudFront offering. This means whenever someone tries to DDoS you, we have a lot of countermeasures we can deploy to avoid a DDoS being successful. The first one of those is very easy to understand. It is very hard to bring down a service like CloudFront. It's very, very expensive. If you're doing a DDoS, you're hiring a botnet or something like that, you're going to be spending a lot of money before you can successfully bring down CloudFront because of its sheer capacity. Even if you can affect, let's say, a small point of presence or something of that nature, we can manage traffic in a way that will send this attacker only to that place or redistribute the traffic and make your distribution available. Your content will always be available. CloudFront also includes Web Application Firewall, which will protect your content for common attack scenarios like cross-site scripting, SQL injection, and many others. CloudFront will always keep its servers up to date, so you don't have to worry about, am I running the latest SSL library that has protection against whatever new exploit has been released last week. We are. That's our job. We do that for you. We are announcing in this week, I don't know if that's probably the first time you're hearing it, a product called field level encryption. With this product, we're going to hold the public key you're going to give us, and we will encrypt some fields inside a form in a post or put request with that public key, which means your personal PII data, which is personal identifiable data, will be encrypted from the very first point of contact on the CloudFront network until the very last point where this data is consumed. So who uses that today? Amazon again. Whenever you put the credit card information, whenever it touches CloudFront, that credit card gets encrypted. So there's no way it's going to be end up in a log. There's no way it might be inspected by a mid-level service, because it flows through a very long pipeline of services, but only the payment service needs this credit card information. You can do that for your own data starting a couple weeks from now. And that brings me to compliance. If you use field level encryption, your surface area that has to be audited for PCI compliance is greatly reduced, because now all these intermediary systems, they don't see your data. They see just a blurb of encrypted data and then don't have the key. So as long as you can prove you are correctly managing this key, you don't even have to audit this intermediary system. It's much easier to get PCI compliance. By the way, CloudFront will enable you to have PCI compliant, HIPAA compliant, DSS compliant systems. All our infrastructure is PCI compliant. So you can build a PCI compliant service on top of that without having to worry about the security requirements that are posed on data centers. So, by the way, we care about those in reverse order. So I presented them in performance, availability, security, but our concern is actually reverse. Security for us is more important than everything else, then availability, and lastly, performance. So now let's get to the reason we are here, measuring the internet in real time, right? So this is how a request flows through CloudFront. So our viewer there wants to get a GIF for a cat. So he goes to his ISP DNS resolver. That's going to be Verizon, Comcast, or whatever could be your ISP, and ask it for what's the IP address for example.com. This ISP resolver will eventually find our own DNS server, and is going to ask distribution.cloudfront.net, what's the IP address for that? The CloudFront DNS system, we're going to have to take this information, the distribution name, the resolver, process it, and come out with an IP address. We're going to give that back to the user, which then connects to our POP and gets his ugly cat. So the problem we are trying to solve here is to how to optimally answer this question. Given a resolver, what is the best POP? Where to send this request? We're going to take all these factors in consideration: performance, server capacity, POP health, and network capacity. We want to take this all into consideration to give our users the best possible experience. The way we do that has to be done in real time, because the internet is not a place that is always like Las Vegas with blue skies. Sometimes it's like Seattle that has bad weather, right? So you have to account for that all the time. When there is congestion, we have to route around it. When there is interruption, we have to route around it. So you don't have to care about internet weather. We care about it for you. I started this talk saying something about feedback loops. So let me define what I mean by feedback loops. When you're in the shower, you want some temperature that pleases you, right? But you don't want to know anything about hydrodynamics or thermodynamics and calculate how much flow of the hot water is coming, how much of the other one, and that many degrees to get the perfect bath. And then someone goes to the next hotel room and turns the water, and all this is changed. You don't have to do that. You don't have to do any of that. You just have to know one side is hotter, the other side is cold, because you are measuring the temperature on your back all the time. And you can feel it's better or not, or worse, and then you can turn the knob. Feedback loops are based on the same principle. I don't have to understand the inner workings. I just have to understand that if I move the knob to one side, I get this behavior. If I move the knob to another side, I get this other behavior. It's the same thing that we all do when we drive. We move to one side, we move to another, but I don't know how many degrees I'm moving my steering wheel, right? So how does this apply to CloudFront? We have a POP. We take measurements to a central location, happens to be AWS, and we send back to the POP control data. So let's start with the measurements we take. The first measurement we take is the round trip time, right? The 100 milliseconds from here to Brazil. So this is how we measure round trip time. Every time a new connection, a new TCP connection lands on a POP, we measure the time it takes from the SYN ACK back packet we send to the ACK packet we get back from our viewers. So by measuring this time, we have one data point of latency. What we do with that, we send all of this through Kinesis, to an Amazon Kinesis stream. So hundreds of POPs, hundreds of servers inside every POP, tens of thousands of servers worldwide. We push all this data to Kinesis stream. We use Kinesis consumer library, KCL, in EC2. We aggregate all this data, we push it to S3. At the end, what we get is something like that. For every network, we have a list of POPs under latencies. So now we know for every POP, for every network in the world, every network we see contacting CloudFront, we know in real time what are the best POPs for them, latency-wise. Before I continue, let me talk a little bit about the way we use Kinesis. So Kinesis has all this performance, all this ability to push a lot of data from distributed locations around the world. This could be in your applications devices, which are spread around the world. It has this ability because it has the concept of shards. So shards are these sub-pipes inside Kinesis, and you can have as many of them as you need to process your data. In our case, the sharding key, the way we separate the data, is the POP name. So some POPs go into one shard, some POPs go into another shard. When you consume the data, your consumers are also tied to a single shard. So you have to select your key in a way that allows you to process the data you need together in the same consumer. So it's very much like a MapReduce type of processing pipeline, and that's what we build with Kinesis. The interesting thing about Kinesis is the fact that we can dynamically change these shards. So the way it works is that whatever shard key you pass through Kinesis gets hashed and gets transformed into a number from 0 to 200 to the 128th minus 1. And that large key space determines which shard you get. Every shard has a starting number and an ending number. So once you hash it, Kinesis does that for you. You end up in a shard or in another shard. And shards have finite capacity, right? You have to create new shards if you need more capacity. Sorry. So let's say we are building CloudFront from scratch today, and we only have 2 POPs. We actually started with 14, but let's say we only have 2. They both fit in a single shard, so it's fine. We don't need to do anything else. And then comes a third one. Kinesis cannot handle the data of 3 shards, 3 POPs in a single shard. What is it that we do? We do what we call resharding. We split this shard in half. Now, the first shard is okay, the second one is okay too. But CloudFront keeps growing. We now have 5 POPs. What we do, we split the second half in shards as well. When you do that, you don't have to change anything on the consumer side if you're using Kinesis consumer library. It will recognize the new shard, it will drain the old shards, read all the data from the old shards, recognize the new ones, and then starting reading from the new ones all transparently without you having to do anything. As long as you have enough compute power to run this, the service that is consuming this data, you're going to be fine. And how do you do that? Just have an auto-scaling group, for instance, and then you have enough capacity to run, to consume this data. Okay, back to CloudFront. I told you before that the request, when I explained the request lifecycle, that we have to make this decision based on the ISP resolver. The ISP resolver will not tell us the IP address of the viewer. It will tell us the IP address of itself. There is something called ECS that some resolvers like OpenDNS and Google DNS use, but that's not prevalent across ISPs because it's much more expensive for them to provide. So what we typically get for most requests is a resolver IP address and a domain. But if you remember, the data we have is by viewer networks, right? So that's not really the same thing. So what do? So we take these viewer networks and POP latencies, and we transform that into resolvers to latencies. How do we do that? We have another measurement system, which I'm not going to be going to details today, that generates for us what we call the resolvers to viewers mapping. So we have this mapping that tells us which viewers which networks use which resolvers. And then we can do a map-reduce type of operation and come out with the data that we care about, which is the resolver to POP mapping with latencies. Okay, what we've learned so far. We learned that using Amazon Kinesis streams to get data from many distributed endpoints to a central location is something very efficient. We learned that using KCL, the Kinesis Consumer Library, to consume this data makes it easy and simple to build your consumer side of this analytics pipeline. And we also learned something that you already probably know, that you can store this intermediary data in S3. Okay, we also measured other types of data. For instance, we measure POP health. In this case, we're not using Kinesis, we're using CloudWatch. We're creating CloudWatch metrics for the POP health that tell us, for instance, what's the CPU usage on a single POP. And they're pushing this data to CloudWatch. A big advantage of doing that is that we get alarms and we get dashboards just by using CloudWatch, which makes it much easier to get this other data we need, right? And on the other side, we pull this data from CloudWatch using CloudWatch's API, which can give us real-time access to the latest value of all these metrics. And then we can decide, is this POP healthy? Is it taking too many requests? Should I send less traffic to it? Is it taking too few requests? Can I send more traffic to it? And we store this computed capacity in an RDS database. So we do this computation, decide whether the POP is just like the shower, too hot, too cold. We turn the knob, and we store this data back into an RDS database. Another design pattern there is to, whenever you can, whenever the number of metrics allows it, use CloudWatch metrics instead of Kinesis, because then you get alarms and dashboards without having to do any further work. That makes it much easier. And another one is that you can read these metrics from CloudWatch using an API. You are not tied to the console. You can have this data inside your feedback loop automated system. So I told you about other types of data. I told you about link utilization. I talked about load by viewer network resolver. We follow the same patterns there. So we use either Kinesis or CloudWatch. So I'm not going to go into detail. So how is that all put together? So we have the input resolver. We have all these auxiliary inputs: performance, server capacity, POP health, network capacity, and we have to decide which POP. And I told you you're going to be using feedback loops to do that. So putting it all together, we have the CloudFront POP, which, by the way, also hosts our CloudFront DNS service. And we push all this data, RTT, latency, load, and link utilization over Kinesis. And we pre-compute a resolver to POP association table. We send this table back to the POPs, to every single POP in the world, so that they know when they get a resolver to which edge location to send this request. And we do that continuously. We keep building those all the time. We get new data, we build a new table, we send it to the edge. We also have the POP health feedback loop on top of that reads health metrics and store those into, and process that using EC2, store a capacity value inside RDS, and then that feeds back into that first system telling us how much load a POP can take. Can this POP take this much load? Should it take less? And that also feeds into the pre-computed resolver to POP table. So another design pattern here is that we can use multiple nested feedback loops. And that is good, because that allows you to take a very complicated problem, like the problem statement I had before, having all these inputs to decide to which resolver, to which POP to send every resolver, and boil it down to a simpler problem, to a problem that I can understand. And then another feedback loop on top of that, and it's also a problem that I can understand. And the resulting system is very complex, but it's one that I can understand. We also learned that we can pre-compute this data in AWS, so I don't have to do any kind of expensive computation every time I get a DNS request at the edge, because it would take too long, and I have to do that millions and millions and millions of times. Okay, so let's see that in practice. How does that react to ever-changing network conditions? So this is how routers work these days. They have all these input interfaces and output interfaces. They're usually the same, but let's understand them as being separate. Every time a new IP packet comes into a router, it decides in which part of this cross network to connect them and send the packets to the output. You can see that you can have the 3 inputs sending data to the same output, and it would not be able to process that or to send that because there's finite bandwidth on every single one of these arrows. So in practice, the way it works is that it has a buffer, a queue, on every single one of those outputs. When there is congestion, this is what happens. Eventually, this queue starts filling up, and eventually the last packet doesn't fill, it gets dropped. So that's how congestion happens on the internet. And then TCP will adapt to that, and other protocols will adapt to that, and we'll send less data to avoid this congestion in the first place. But how do we adapt to that when we see a congested link? How do we see it in the first place? So this is one of those RTT measurements that I showed you before. When there is congestion, suddenly that first pop that was 20 milliseconds is now 50 milliseconds of latency, 50 milliseconds of round-trip time. This means pop number 1, which was preferred, is not preferred anymore. Traffic is going to flow to pop 2 and pop 3 before it flows to pop number 1. So by measuring that in real time, all the time, we can route around congested links. We can send the traffic to whatever pop is best for your customer right now. Remember, congestion usually does not happen inside Amazon network. It happens more often outside Amazon's network because there is much more internet outside Amazon's network than it is inside our network. So we don't have a way to directly measure that, and we don't really know what paths exist inside every single ISP in the world, but you can see the net effect of this increased latency because there is all this queuing happening at every single router along the way. We can see this increased latencies piling up, and then you see, okay, so let's switch links, and we do that without any operator intervention. We do that in minutes. How do you react to a pop getting hot? By getting hot, I mean getting more requests per second than it can handle, or by getting closer to what would be the proper limit of it handling requests with the one acceptable level of performance. So this is how it happens. First, we see the server getting hot. That's a metric, like CPU utilization. We push that to CloudWatch. That lands on EC2. And then EC2 tells RDS smaller capacity, send less traffic to that pop. And then we send that to the inner feedback loop. And eventually, when we pre-compute this resolver to pop association table, we have less resolvers for that same pop, which means less traffic is going to land there, and eventually the pop is going to be okay. It's not going to be hot anymore. So we're going to be controlling for capacity as well with ever-changing loads. So whenever you have a new release, a new software update, a new game update, whatever it is, you send more traffic to us. You don't have to tell us in advance. We're going to sense it and adapt to that. So we learned that CloudFront does all this real-time measurement to be able to give your customers the best performance, the best availability, and the best security in real time. As a recap of the design patterns we talked about today, we learned to use kinesis to transfer data from many different endpoints back to a central location in a very scalable way. We learned that using kinesis client library, we can do that in a scalable way inside EC2 as well. We can consume this data. We learned to aggregate this data in EC3, in S3. We learned that we can use CloudWatch for metrics for when we have low and moderate cardinality, which is the number of metrics is not too large, which would be in the first case. We learned to use multiple feedback loops, so we can take a complex problem and break it down into more simple problems. And we learned to pre-compute data in the AWS region, so we don't have to do all these expensive computations with all this data at request time. And that saves, in our case, That makes the DNS fleet smaller than it would be otherwise, and it makes the DNS response time faster than it would be otherwise. It's a simple lookup. It's a short talk. That's what I had for today. I'll be taking questions from you off stage. Feel free to come by and talk to me. It was a pleasure talking to you. Thank you.